Right, so that was about the choice of a number of blows in the laboratory. But when it comes to the field condition, you can have two things. If you want to have a heavy compaction, you need to have a big hammer in the laboratory. And when a big hammer is used, the soil should be filled in 5 layers, right? Likewise, if the field condition demands just a light compaction, you just have to use the standard hammer. And if a standard hammer is used, you just have to fill the soil in 3 layers. So essentially, it boils down to one simple principle. If you are using a heavy compaction, use a big hammer and 5 layers. If you are using a light compaction, you have a standard hammer and 3 layers. So the choice of the number of layers depends on the heaviness of the compaction, whereas the choice of the number of blows depends on the particle size. Now, once you've completed the laboratory test, what you get are 2 things: water content and dry density, right? We started with 4% water content. You get a dry density corresponding to that. You have an increased water content, let's say 6%. You have a dry density corresponding to that. Likewise, what you have once the complete test is finished is that you will have a set of water content values and dry density values, based on which you'll draw a graph, a water content versus dry density, right? You have water content on the x-axis and you have dry density in gram per cc on the y-axis, and the plot would look something like this, a bell-shaped curve, which means as you increase the water content, the dry density increases up to a certain limit, and then an increase in water content decreases the dry density, right? Now, there's a maximum value here, a maximum value of dry density corresponding to which you have a water content, right? So this point is the one that an engineer is interested in at site, let's say of highway construction, right? This value gives the maximum dry density. Soil will be completely packed, stable and strong, right? So this is the one that we're interested in. So that peak point is called maximum dry density, MDD, and the water content corresponding to the MDD is OMC, optimum moisture content. So you have maximum dry density, which is attained at a water content of optimum moisture content, right? Now, what you did is you draw a curve with the water content in x-axis and the dry density in y-axis, which is called as a compaction curve, which is typically a bell-shaped curve. And this gives an idea that with an increase in water content, the dry density initially increases, and on reaching a peak point, it starts to decrease with further increase in water content, right? So the density corresponding to the peak is the maximum density, and the water corresponding to the point is OMC. And at any water content which is less than OMC, you have OMC here, and you have the water content less than OMC in this region, it is called the dry of optimum region. And any water content which is greater than the OMC is called the wet of optimum. Wet region, dry region. Now, any water content less than OMC, what happens is that the soil is stiff and the void spaces are usually filled with air, and the density is less because the density of air is less than the density of water, right? For that simple reason, whatever soil that happens to be on the left side of OMC has a lesser density, right? But what happens when you increase the water content beyond the OMC is that water starts to occupy the space that might have been occupied by soils earlier. So essentially, once we increase the water content above the OMC, the water tries to replace the soil, right? So it further decreases the density. So the reason for the decreased density here and the decreased density here are quite different. Now, there comes a theoretical idea called ZAV, zero air voids line. Now, since compaction is a practical process, you can't actually remove the total air voids. Hence, the soil never attains a fully saturated state wherein you don't have air, right? There's no such practical case using compaction. You can't attain fully saturated state using any sophisticated compaction method. But there's a theoretical line indicating a case of maximum dry density or fully saturated state with air voids equal to 0, right? So it's written theoretical because it is a pure theory thing. That line is called a zero air voids line because it's a line which represents a soil state where the void ratios, the air voids is 0. You don't have air in it. Such a condition is represented as a zero air voids line. It's also called as a 100% saturation line as well. You can have ZAV here, there, right? This is ZAV. This is the maximum attainable value in the laboratory, and this is a zero air voids line, or the theoretical zero air voids line. Now you know the famous equation rho d, which is g by 1 plus c into rho w, which is nothing but the equation that gives s equal to 0, right? Once you have g plus sc by 1 plus c into gamma w rho w, if you substitute degree of saturation s equal to 0, what you get is g by 1 plus c into rho w. Now in that equation, the voids ratio E can be replaced by Wg by S, because you have an equation called Se equal to Wg, the second or the third equation that we studied. You use that and replace E, voids ratio. So what you get is G by 1 plus Wg by S into rho W. But we were saying that ZAV is also called as 100% saturation line, which means S is equal to 1, right? So I can rewrite the equation as G by 1 plus Wg into rho W. Also, I can rewrite that equation in a different representation, 1 minus Na by 1 plus Wg into G rho W. So these two equations will help you to solve the problems related to the zero air voids line and the compaction. Now there's another thing called compaction control in field. While starting the module, we were discussing that an engineer at site is interested to have his soil compacted to the maximum attainable strength, right? Let's assume take the example of a highway construction. You want the road to be strong. You want the road to be constructed on a soil subgrade which is quite strong and compacted to its maximum potential, right? So for that purpose, you have taken a soil, you have carried to the lab, you have tested, you have tried to see at what water content will the soil attain the maximum dry density. Now that's about a lab determination. You are trying to implement that in the field, right? So you have already conducted a lab test, you have found out that, let's say, 1.8 gram per cc is the maximum dry density, and you need to add 14% water to get that maximum dry density. Let's take that example. So that 14% and 1.8 gram per cc is what you've got from your laboratory. Now you're trying to implement that in the field. You should have a control and a control system in which you can check the water content and the dry density to ensure the quality control, right? Which means a specified amount of compaction with the OMC is to be ensured to attain target density. To check the density, you can use the methods like core cutter and sand replacement, or perhaps nuclear methods. Now these core cutter and sand replacement methods are the tests that you're about to do in your subsequent semester. You will have to visit the lab and do such tests to determine the density. But to check the water content, oven dry method is the best choice. But the problem with the oven dry method is that it could consume almost 24 hours to give you the result, and it's not advisable for field condition. You don't have the luxury of time in the field to test the water content by waiting 24 hours, right? You'll have to take decisions on the site. So in such conditions where you don't have the luxury of 24 hours in hand, you go for what is called as a Proctor needle method to check the in situ moisture content, right? So in short, you can use the core cutter, sand replacement method or nuclear method to get the density at field, But to evaluate the water content at field, you go for the Proctor needle method. Now this is a picture of the Proctor needle used in field, the discussion of which is given in this slide. Now you can see two people trying to squeeze something or jack something into the ground. This is a Proctor needle. These two guys are trying to jack this needle into the ground. You can probably understand, it's quite simple to understand that the resistance offered by the soil is kind of a representation of the water content there at the soil, right? So that principle is employed here. It fundamentally has got a sliding ring, a stem, a needle shank, and a needle point, right? This picture gives you the parts of that. You have a sliding ring here, you have a loading plunger, you have a needle, and you have a needle point. And above the sliding ring, you have graduations marked there, which gives you the reading from the Proctor needle. Now, the actual picture looks something like this, about 1.8 meters, as you can see from this figure. Now, the sliding ring on the stem reads the maximum penetration resistance in Newton, right? The resistance offered by the soil is given by the sliding ring in newtons. The needle shank indicates the depth of penetration, and a needle point of suitable area is chosen based on the soil type. Depending on the soil type, the engineer at site chooses the needle, the type of a needle, and after the compaction of the soil at site, let's take the same example. A highway is constructed, and once the compaction is completed, the needle is forced 7.5 centimeters into the ground. Quite similar to the picture that you can see to the top right corner, right? It's the people are trying to squeeze that, jack that into the ground for a distance of 7.5 centimeters. Now, the maximum force required to penetrate 7.5 centimeters is obtained, and the penetration resistance is computed per unit area, right? And once you have got the penetration resistance in per unit area, you can use this calibration chart, which means for any penetration resistance, you can get the water content from this calibration chart. So what you get from the field is the penetration resistance, and using the penetration resistance from the chart, you get the corresponding water content. So that's a field method in which you can estimate the water content.